So thank you very much for coming, everybody. This is a session about practical mobile app attacks by example. All the in the demos, I'm going to show like some vulnerable applications and some vulnerabilities. So these are all available for free. This is not just a webinar, but also a workshop. So you can access all the applications that I'm going to demo for free, the slides, the recording. This is all on 70security.com/free. So if you can go there and you can download everything. This workshop and also there's other workshops there that we have if you are interested. Um, okay, so let's get started. I'm Abraham Aranguren. I'm the CEO of 70 Security. We have delivered training at Black Hat USA, Hack in the Box, OWASP, Global AppSec, NullCon, Hackfest, and many other conferences. I've done stuff for Q53, version 1, eLearn Security. I wrote this course a while back for them for practical web defense about hacking and defending web applications. I'm the founder and one of the project leaders for OWASP OWTF, which is an OWASP flagship project. So if you type in your browser owtf.org, that takes you to the OWASP project, which is also completely free. If you are interested about web security, this is my slide and some certifications. So the certifications, the background here is that I was a developer first, and then I switched to security, so I kind of can speak both languages, let's say. So if you're interested about this presentation, I think I think this slide is going to be interesting, right? Because the first half of the slide is about Smart Sheriff. So this was an application mandated in the entire country of South Korea. So by law, every parent and child in the country of South Korea, this is the good Korea, right? Not the communist one. So in this country, every parent and child by law was forced to install this application. So the idea was to help parents be parents. So a parent would control during what times of the day the child can access the phone, what applications they can have installed, what websites they can visit, and stuff like this. So in theory, a very nice idea to keep the children safe. In practice, horrible security implementation, lots of security flaws. So if you search on YouTube for smart sharing, um, uh, smart sheriff dumb idea on YouTube, that will show you the presentation. So it was so bad that we even gave a talk about it, right? And also you can check these two public pen test reports. So reading public pen test reports is a very good way to learn about security. So this is pretty much everything you should never do when you implement your mobile application. You can find that in these two reports, and we will go over some of the findings in this presentation. And then the Chinese police apps, the background here was to help human rights activists to figure out if something was a human rights violation or not. That was their decision, and we just helped them on the technical side trying to find evidence. So very quickly, BXAQ is an application Chinese police use when you cross the border of China. They install it in your phone, they grab your contacts and all other stuff, and then they push the data into a police server. iJob is used by police officials, particularly in a region of China called Xinjiang, where there's a Muslim minority in theory to reduce the chances of terrorism. And then Study the Great Nation is an application that is not mandated like Smart Sheriff, right? So this is kind of voluntary. However, it is encouraged because the more you know about the great leader of China, the more points you get. And then with these points, you can do cool stuff in China, right? So that's the idea of those three apps. So if you search on YouTube for Chinese police and cloud pets, you can see a talk about that and the slides. And there's a lot of other pen test reports on the website, so you can go through these and learn a lot about mobile security there. So we're going to see some interesting attack vectors found on mobile applications over the years. So I hope you find this workshop entertaining. So let's first start with something maybe familiar to everybody, XSS, right? So web views and data exfiltration. Let's start with Android. So a web view is basically a small browser that the application has. A web view is going to have as many permissions as the application that includes it. They can be explicitly enabled to execute JavaScript and can load local files as well as remote web content, depending on the settings. And then sometimes this native Android functions can like sometimes access like Java code using JavaScript interface. So this could sometimes get interesting as well. So what can we do attack-wise? Right? So we can do HTML injection, which doesn't sound very, scary. However, in a mobile device, since you don't see the URL bar because things need to be pretty, the screens are small, and so on, with HTML injection alone, if you can craft a page that is like a believable login page, this will, you know, could be very effective, right? So with HTML injection, you can actually do quite some damage, assuming you have like, decent control on the page. Then with XSS, we can do more stuff like change the page, invoke functionality, and so on. Then sometimes you can also do data exfiltration, which is what we will see today, some of the examples. And then in some cases, you can even like do cross-site request forgery using XSS, but this again depends a little bit on how the application is set up. So for this exercise, we will use a modified version of Androgoat, right? So Androgoat is an open source project. However, if you use the open source project, the demo that I'm going to show now won't work. So you need to use the modified version that we did. This was a reenactment of some vulnerabilities we have found in practice. So we took like an open source application, changed it, and created our own vulnerable application. So you should use this. If you're attending this workshop, you should have access to all the materials already. So just check your email for an email titled Welcome to 7A Security Training. If not, go to 7asecurity.com/free, and there you can get like all the workshops, the slides, the recordings, all the vulnerable applications, everything, right? So it's all there for free. So the way it works is once you log in and download the slides, from the slides while you are logged in, you click on this link, right? So if you wget this, it won't work. You have to click from the slides, and then this will download just fine, right? So just remember all these trainings, cybersecurity.com, just click from the slides so that this works. Okay, so first, since we're going to do data exfiltration, first we need to create some data files, right? So you go to insecure data storage, share preferences, part one, and then here we add like my secret user, my secret password, we hit save, and then we need to do the same with SQLite database, right? So we go to SQLite, my SQLite user, my SQLite password, whatever, and click on save, and then we should be able to, start playing with XSS. So first we go to input validations XSS. This will make more sense when I show the demo, but as you go through this, it will make more sense as well in the demo. So first we're going to check with h1 hello. So this should show like a bigger hello if there's HTML injection. So we try that, we see there's a bigger hello. So this means that this is working. Now the next step is to say, okay, we have HTML injection, but do we also have XSS, right? So we can try image source section or alert one, script alert one, and so on. If we get the alert one, then this means that we have XSS as well, right? So now the next question is, what is the security context in which this XSS is running, right? So the answer to that is something we will know with alert location. If we do alert location and you display this, it doesn't matter if you use internal or external storage, they have slightly different attack vectors. And then here you can see that we have a file URL, right? So a file URL is very interesting because it means there's no same origin policy. A file URL is going to be able to read local files and send them to an attacker, right? This can be locked down with web view preferences and so on. But in principle, if you have a file URL, your luck for exfiltrating files from the phone is much, much higher. So in this vulnerable application that we modified, we have two examples, right? Because you could have two possibilities. One possibility is that the affected file is on the internal storage. So this data directory is something that other Android apps cannot access. And then the other possibility is that it is on the external storage, right? On the SD card. So If it is on the SD card, then this is more risky because any other application on the same phone can write there. So you have like XSS by definition, basically, right? Even a physical attacker could extract the SD card, modify the HTML file, and then gain XSS on the phone, on the application that way, right? Then, since we're doing data exfiltration with XSS, we need to figure out what is the location on the file system of the file that we want to deal. So one way to do that could be to do adb shell, and then you cd into the directory of the target application. You run the find command, for example, that will show you all the files. And in here, we can see share preferences, users, XML, and databases, AGOT, right? So with that, we can do like script, then new XML HTTP request, and then get the location of these files. And then if this works, we should be able to get an alert that renders the contents of this file, right? So we should be able to see something like this when we try this. Um, and then another possibility is to steal system and third-party files, right? So we can use, for example, the configuration files from the phone or even libraries from other applications, as long as the permissions allow any application of the on the phone to read them, right? So we need to know the full location of the file that we want to read with XSS. But otherwise, as long as the application has permissions to read it, we should be able to read it and steal it, right? So this is the configuration file, and this is the library from the other app, right? So we can do all that. So yeah, I explained all that. So first, methodology-wise, we're looking to answer these questions. So yeah, do we get the alert one? This means we have XSS. Alert location shows us the context, so it's a file URL, so more privileged. And then we have here like the other payloads to read the local files, right? Users XML, the SQLite database, and so on. This all works because all these insecure settings are set. Now by default, this does no longer work on Android. Believe it or not, this was the default until Android 4 something. Nowadays, the developer kind of has to shoot themselves in the foot with this. So they have to like enable all these things. But otherwise, this attack remains possible. It's just less common nowadays because it's not the default, right? And then the other problem is that we have file URLs in there. Let's do a demo about this. Let me see if I'm sharing my entire screen. Okay, share my screen, which I should. Okay, so let's do the first demo, XSS and data exfiltration on Android. So what we're doing here is we're trying to read the different files, right? So this is reading the secret password. This is reading the SQLite file as well, right? So we can basically try the payloads there and do that, right? So we're basically just copy pasting the payloads from a website in there. You also have like a website with all these payloads from where you can paste them in the slides, right? So that you don't have like to type the whole thing and so on. Okay, so that's this demo. And let's continue because we have a lot more to go. So now let's do the same on iOS, right? So iOS is basically the tag is kind of similar. We will use them vulnerable insecure version 2. So you go to web view issues, start challenge, and here on what's your name, we will be trying the payload. So very similar methodology. Hello one with hello with h1 tags. It's going to show appear hello. And then we can try alert one, alert location, and then try to read some local file, like for example, the contacts or the data usage or stuff like this from like known locations on iOS, right? Their script otherwise looks the same. What's going to change is the path. And this is more or less how this looks, right? So this is the alert one, this is the alert location. In this case, instead of a file URL, we have an Apple Web Data URL, which means basically that we have, file privileges. It's kind of the same as on Android, the file URL. In iOS, you could also have a file URL, but both file or Apple Web Data mean kind of the same thing, like danger. like you should be able to read local files, especially if the application uses UI web views, as we will see. And this proves that we can read SQLite databases from the XSS as well. Methodology-wise, same questions. Can we run XSS? If we get the alert one, yes. The alert location, if we get Apple Web Data or file, that's exciting. And then usage, cellular usage, and there's other places on the phone, known locations on iOS that we can try to read. This is the vulnerable code. So this is a string concatenation in Swift, which is kind of interesting because here it is not breaking out of the quotes. It's like a backslash, so this can be a little bit weird for those unfamiliar with Swift. And then the problem here is that this is using a UI web view, which is vulnerable by default to this attack. And the base URL is empty. So when the base URL is empty, the UI web view defaults to file permissions or Apple Web Data, right? So that is the problem. Because it is Apple Web Data or a kind of a file URL, then this is what is allowing us with the XSS to exfiltrate local files, right? So this issue required WebKit allow universal access from file URLs and WebKit allow file access from file URLs, which both of which are turned on by default on UI web views and disabled by default on WK web views, right? So Apple now recommends to use WK web views because of this, but until iOS 13, which is relatively recent, like a couple of years ago, UI web views were kind of, common. And now I think that they are deprecated, but you can still use them, right? So they are not like completely eliminated. So many old iOS applications will still be vulnerable to this, right? So let's do a demo about this. So this is the iOS XSS with data filtration. So we're just copying the different payloads. So this is the script alert one. We get the script alert one, right? Now we can try SVG on load alert location just to see what is the security context in which this is being rendered. And we can see that this is the Apple Web Data context, which is more privileged, no same origin policy, ability to read local files, right, for our purposes. And then after that, we can try to read local files. So this is just trying that. Um, and you can see that we can read the SQLite databases from the phone and so on as well, right? So, okay, so that's enough. So let's continue, right? So the problems with the SD card are, so the SD card is kind of the Wild West in Android, right? Because many apps can read and write here. It can be extracted without unlocking the phone. There's no encryption. So, lots of things can happen, right? So if you have a malicious application installed on the phone, then many apps can read and write there. So that's bad because, you can like write some HTML that then another application loads and then you have XSS and things like this. It can be extracted without unlocking the phone. So even a regular thief can like extract the SD card and read whatever it's on the card, right? So this is like no security. You don't even need to unlock the phone or anything. And there's also no encryption, right? So by default. So this is kind of a problem with the SD card on Android. Um, so let's get started, right? So some example of saving sensitive stuff on the SD card. This was a whistleblower application. So in a country where basically the government is against the population, and then some human rights activists developed this app that to help citizens to report human rights violations to some NGO. However, the implementation was not so good because the human rights violation reports were being saved on the SD card. So in a country like this, what could happen is that a police officer takes your phone, extracts the SD card, plugs it into a computer, then they notice you are reporting on these human rights violations, and then you go to prison, get killed or tortured or whatever, right? So this could be, it's a security vulnerability that could turn into nasty things in the real world, right? So this was all the data that we're gathering with that. And now this is another scenario with text files. So in principle, looks like not harmful, right? Loaded from the SD card. So this is loading a chapter from the SD card, then this is stored in a variable, and then the variable is concatenated into HTML, resulting in XSS, right? So using hack vector, which you can use in a browser. This is by Gareth Hayes, a friend of mine. He works for Burp now, so there's also a Burp extension for it. Um, so this has like a lot of encoding and decoding tools, so it's very handy. So you can, when you have trouble with like quotes and single quotes, and the code is, not really working, you can try stuff like this, right? So you can eval from charcode of the payload, right? So a new XML CDP request, and then we read some database from the application, and then we encode all these with eval from charcode. So this results in script eval string from charcode, and you can see there's no single or double quotes here. So then this allows the payload to work against the application. So this was the alert at the time. Um, then let's continue. Now, other types of attacks are spoofing attacks. So one possibility is that you show one URL, but then when the user clicks on it, they really go to another URL, right? So this can be interesting to obfuscate some attacks. And you can achieve this with right to left and left to right characters sometimes. So for example, you can send a link with these characters here and then mock.evil.org. So the victim is going to see grow.live.com, but then when they click on this, they really go to mock.evil.org, right? So they're reversed basically. So you can try to use this against email apps, chat applications, and stuff like this. And this is like some report of this being used in the wild. So it's an interesting attack vector. Now, something most people don't think about when they test a mobile application is that sometimes mobile applications implement local servers on the phone, right? So you should check with Netstat, like what are the services listening before you run the app, then what are the services afterwards, and then do a diff to try to see like if the application is opening something, if you're doing things black box, for example, right? In this case, this was a Cordova iOS application. It used a plugin that was running a local server, and this local server was vulnerable to path traversal attacks and did not require authentication. So a malicious application on the same device would be able to, like use the path traversal to read like arbitrary files from the phone with the security privileges of the target application, right? So you can see these localhost and so on, right? So, but just by knowing the port, and then you can just do this, right? So these are some examples of what you could do with this issue. So it was an interesting bug, right? So you could like weaponize this and dump all the files like this, right? So with that, a quick question to the group: do you believe cross-site request forgery exists in mobile apps? Right? So you are probably all familiar with cross-site request forgery on the web world, but does cross-site request forgery exist in mobile apps? What do you think? Yes, no? Any takers? Yes. So yes, you are correct. So we can achieve cross-site request forgery typically with deep links, right? So deep links are interesting because this is a very recurring pattern. They are very common. Lots of applications use deep links, and there's a lot of bug bounties awarded for this, right? So let's see some deep link attacks achieving user impersonation and deep link attacks to bypass authorization controls. Deep link is basically a URI that can be used to navigate to different parts of an application. Both Android and iOS have this, and deep links can have, but do not need to have custom schemes, right? So, for example, a deep link could look like social app colon slash slash homepage, or the same thing, profile picture. So it's basically a URL, and then when you open this URL on the mobile phone, it's going to take you to a certain screen on the mobile application, right? So that is basically the idea. And then when you're doing this on Android, um, what you can do is to look for browsable activities, right? So deep links do not necessarily require the activity to be browsable. However, if it is browsable, then things are more interesting because it can be attacked from the browser as well, right? So browsable browser, that's a quick way for you to remember this. So one way in which this can happen is that you have an activity, then you can notice that here there's no exported true anywhere. However, the activity is implicitly exported because it has an intent filter, right? So when you have an intent filter, this means that any other application on the phone can attack this activity, right? So that's basically the idea. And then here, this is browsable, so it can also be attacked from the browser, not just malicious applications on the device. And then this is the structure of the deep link. So in this case, we have a scheme, some app, a host, get creds, and then path prefix user, right? So this translates to some app : / get creds user. So that's the structure of the deep link, right? Based on this. Now, in some cases, you won't have browsable, but there will still be a deep link that other applications could attack. And you might not have this, and then the application does this through code, right? So it can be done either way. So don't just rely on this. This is just one way in which applications can do it. There's, always no replacement to look at the source code as well of the activity itself, and that could give you more hints. Also, don't forget to look at the code of the activity that you're looking at inherits, because sometimes the relevant code is there, right? So it's also interesting. Okay, so for this next demo, we're going to use a Periscope cross-site request forgery. This was a real vulnerability on a very popular Android application. So to download the vulnerable version, you can get it here. This is the direct link. So you need to kind of use the vulnerable version for this to work. Then you basically create an account, log in one of these ways, and then methodology-wise, you would first look at the Android manifest. So first we have to decompile the APK. One way in which you can achieve that is with APK tool D for decompile, and then the APK. So this is going to give us the APK, and then we can look at the Android manifest, right? So if you look at the Android manifest, we can see lots of intent filters, browsable activities, Android host. So all these things are giving us hints about the structure of the deep links and so on, right? And the exported activities. So not browsable equals only attackable from malicious applications on the device, and browsable means it's also attackable from websites, right? So browsable browser. So quick reminder of that. And then there's several ways in which we can do this, right? So this is, so one thing is to do the ADB command, right? So we can launch the command with a deep link like this. Another option is with Drowser. So with Drowser, you can run the scanner. So it has a scanner for browsable activities. Now you will notice this is not very comprehensive and it misses some activities. However, it is still an automated starting point, right? So you should always use it. Just remember, this is not all. And then for the actual cross-site request forgery, we need to add the following to the deep link, right? So this is the vulnerable URL is pscp : //user, then the ID of the user, and then the actual vulnerability is when we add the follow, right? So what happens is the application goes to the user, but it also follows the user without user consent. So a malicious application on the phone or a malicious website can send a deep link to the user that when opened by the app is going to follow any user that we specify here without any user interaction, right? So that is the cross-site request forgery. So you can do that with deep link tester, right? So you do here the follow, go to URI, and you can see that you're following the user. You can do it with ADB shell, right? So ADB shell and so on. And then you add the follow there. And then with Drowser, this would be the equivalent, right? So run app activity start, and then you send the deep link with the follow as well. Since the activity is browsable, you can also use this URL here that has like the payloads to demonstrate the attack from a browser. So you open that from the Android browser and then click on the Periscope cross-site request forgery demo, and that will also work, right? So you click on Periscope cross-site request forgery demo, and you will notice this will change to following as well, right? So we are basically able to follow arbitrary users with this. This is the HTML of the page. So basically, open user doesn't have the follow, and then the cross request forgery is when you add the slash follow at the end. So let's do a quick demo of this. So basically, we're trying first deep link tester. We add in there the slash follow, then go to URI, and you can see we change to following. Now we have to unfollow and minimize the or click on something on the application so that we are no longer following the user, and then we can try, with ADB shell, right? So we do ADB shell, Android intent action view, and then we pass the deep link with the follow, and then when we open the phone, so this was demonstrated on a real phone. This is because there were some invisible characters. So so you can see that it changed to following, and then you can do the same with Drowser as well, right? So you first unfollow, click on something else, and then you can go to Drowser, and then you can see that this changed to following as well, right? Then from the website, we're basically just opening a website on Android. So we are unfollowing, then click on something else, and then click on the Periscope cross request forgery demo, and you can see that this changed as well to following, right? So that's, I think, of that. So deep links are interesting, right? So now let's see deep link attacks to make phone calls, right? So for this, we will use the vulnerable insecure version 2. You can get it from the open source website, or you can get it from the training portal. And in here, you're looking for URL schemes, right? So you have URL schemes, then vulnerable insecure, then vulnerable insecure Swift. This is on the info plist of the application. So this is going to give us some hints about what the deep link structure is. In this case, we only know the URL scheme itself, but we need to look at the source code to see the rest, right? So another way, instead of looking at the info plist, if you have the source code, is to click on the project from Xcode, go to info, and then you scroll all the way down to URL types, and you see here the URL schemes, right? So then vulnerable insecure, then vulnerable insecure Swift, and then to look at what comes after the URL scheme, we need to look at the app delegate, right? So we have the app delegate.m. If the application is written in Objective-C, if the application is written in Swift, it's going to be app delegate.swift, right? So just find app delegate.swift, and then we can look at the source code, and this is basically the problem, right? So the application source code has this. So this is the function. When the application is open, this is the URL that is passed to it. The URL is split into chunks. So this is basically the equivalent, if you are familiar with PHP, of explode. If you are familiar with Python, this is the equivalent of split. Basically, this is looking for the phone call number string on the URL passed, and then it's going to split the string into chunks. So the URL scheme is going to be to the left, so this will be position 0 of the array, and then the number is going to be to the right of this, so this will be position 1, right? So then it's going to cast the number to integer, and if this works, then it will try to call this number, right? So that is basically the logic here. So if you click on appdelegate.swift, this is how it looks, the same code from Xcode. So application, this is the split URL, this is the cast to integer, and then the phone call afterwards, right? So with this, after looking at the source code, we know the structure of the URLs is like this. So then vulnerable insecure Swift, phone call number and the number, and then vulnerable insecure app, phone call number and the number, right? So you can go to this URL, open it on your iOS device, and try these URLs from there. This is the simple HTML on that page for demonstration purposes. And then when you click on this, you will get a dialog like open in vulnerability secure version 2. And when you click on open, it will show you, that the call is being made, right? So let's do a quick demo about this. So this is the iOS device. We go to this URL that I mentioned, and then we can click on the links. And then when you click on open, this will be open on the application, and you can see that this work, right? And the same, if we click on the other URL handler, we're going to get the same alert, and we're basically getting the call working, right? So now let's see other scenarios from the field, right? So from the wild. So URL. What happens if you send a deep link to an application, but the application is a browser, right? So a browser is supposed to open, any URL that you pass to it. So what could go wrong with that? So in this case, we had an application that had browsing functionality. So it actually expects other apps to send URLs to it, and it opens those URLs and shows them to the user. So this was an implicitly exported activity with an intent filter here. Now you can notice here that there's no structure of the URL or anything. This was all done inside of the code. So just to mention what I said before, that don't rely on this for the structure of the URL. This is one such example where the structure of the URL, you have no hints. On the Android manifest, you have to look at the code. So this is basically what it's doing, is looking for an intent extra called search query, then it assigns it into a URL, and then it will try to load it. So we can send a deep link that goes to the SD card and steals databases because the regular expression with which this was being validated allowed file URLs. So you could have a malicious application on the phone that writes an HTML file to the SD card and then sends a file URL to this browser application that is meant to open these URLs. And then will navigate to the HTML file on the SD card, and from there you can read local files, data exfiltration, and so on, right? So we are putting together the deep links with the XSS that we saw before. So this is the actual attack code from the test vulnerable application, the attacker application. So this is the string URL. So for example, mount SD card steal.html, and then put the intent extra for the query, start the activity, and this was basically, getting the application to open the steal HTML, and from here we can read the local files, right? So this is all the databases, and then we read the files and so on. So this was the alert at the time. Now another scenario would be like a browser application goes to an attacker website that goes to a deep link. So in this case, this was the Onion browser. So this is a public report, so we can say the application. And basically, the Onion browser, if it is browsing to an attacker control website, the attacker control website could have HTML like this, like image source, Onion browser, force quit, and then the application would close, right? So without user interaction. So this is a very interesting attack where from HTML that the application loads, you can mess with, the functions of the application using deep links, right? So it's another interesting attack vector. Now, another interesting thing to all this is to use a deep link to then exploit a SQL injection and then turn this into remote code execution. So let's see this, right? So this was a CRM application with Google authentication. So when you open the application, it shows you a pop-up to log in with Google, right? And then when you log in with Google, the pop-up closes, and then you redirect it back to the app, and you use the app as normal. However, this was vulnerable to SQL injection, and then we can turn the SQL injection into code execution. So let's break it down. On the Android manifest, we have a login web view. In this case, we just have the Android scheme. Now, this would be another case where you actually had to look at the source code to figure out the structure of the deep link. And here we can see that this is updating the credentials. with the token that arrives from Google after authenticating. So there's absolutely no sanitization here. We have a string concatenation, so we have SQL injection on a mobile application, right? So what can we do with this? We can first create a bad binary as a proof of concept. So we can go, for example, to data, just trust me. So just a random application on the phone. And then you just echo a lot of A's and save it to a file called test.so. This is important because it's a library that we will use to prove the code execution. Then we give it writable permission, but basically permissions for everybody. And then we can send an intent to the vulnerable deep link activity with the data exploiting the deep link, right? So this is the vulnerable app, this is the data doing the where and load extension and so on. Now this is with URL encoding. I'll show it here without URL encoding. Basically on Logcat, you could see the the string after the concatenation. So you can see there's an Android runtime exception. DL open failed, right? So it's trying to load the test.so library because it has bad elf magic, right? So this means that the magic bytes in the binary are not good enough for, they are not good because it's basically just a lot of A's. It's not a valid library. However, it is trying to run it, right? So this demonstrates that we have code execution, which is pretty cool, right? So this was a very nice vulnerability. And then another attack variant, since the activity is browsable as well, is that we can deliver the library with a page, right? So this is the attacker.com and then some page like a.php basically just sends the file, and then we can create another attacker page, which is really the page where the user would navigate to, that exploits the SQL injection here. So it's doing the where one equals select load extension of the test.so file, which is going to be on the download directory on the phone on the SD card. And then we are loading the iframe that will just download the file automatically. And we wait 5 seconds for the download to complete. And then we will send, we set the source property of the second iframe to, the deep link so that we are basically exploiting the SQL injection and gaining code execution, right? So very nice attack. And of course, we get the same error message. So has bad elf magic because I'm trying to run it, right? So yeah, SQL injection and code execution on Android. Now, regarding URL validation, we're back to the Onion browser. So in this case, this was an error here. This is very common because it's checking that the URL host contains .onion somewhere, right? So location is different than not found. It's a little bit of a stupid comparison, which really means location is found, right? So basically, this is checking if .onion is found anywhere on the string. So not is basically true, right? So this is like a stupid double negation. So this means that is found, right? So if .onion is found somewhere on the host, then all SSL errors will be ignored. So what can we do with this? We can exploit this to ignore SSL warnings. So for example, we could create a subdomain like www.paypal.com.onion.7-a.org, pointing to a Google IP address, and then when you visit this URL from a normal browser, you get security warnings. However, if you visited this URL using the Onion browser, there were no warnings because there was a .onion somewhere, right? So this is a very interesting logic bug that is very common, in many applications, not just mobile, when developers use things like includes, contains, string, and so on. Now, very quickly, some other interesting attacks with XMPP. It's possible sometimes to downgrade to clear text. So when you're doing man in the middle of XMPP, in the handshake, you can specify that the only mechanism to authenticate is plain. Normally, there would be like a challenge response, which would be safer. But if you specify that the mechanism is plain, then the application might fall for this and send the credentials in clear text. This is all just base64 encoded, but you can base64 decode it and you have the credentials there. Another scenario would be attacking updaters. So in this case, we have an update check over clear text HTTP for some JSON file. So we can spoof that and specify that the URL for the update is a phone number. So this is an interesting attack vector on mobile to change URLs to phone numbers. And then you get a message saying that there's a new version available. And then when you click on update, it will basically make a premium phone call, right? So it's an interesting way for an attacker to monetize the attack. Another example, zip party zip file retrieval, right? So we have an info plist with an insecure app transport security exception. So this is a hint that the application somehow requires clear text HTTP traffic to some Amazon domain. So the thing that we can try here is since the zip file is retrieved over clear text HTTP, we can replace it with our own zip file. So when the file is uncompressed, this will replace all the zip files the contents of the zip file can basically overwrite anything that the application is trying to, application files that we want, basically. Now, some crypto attacks. This was a crypto messenger Android app. It's a very interesting attack because the application receives encrypted files. The vulnerability is here. So target file equals new file. And then the problem is with the original file name, right? So new file, original file name. So what can go wrong with that? Since the original file name is going to be used in the file system, we can do stuff like adding a lot of / sequences, and then we have an arbitrary file write on decryption with a / sequence on the file name, right? So user A can create and overwrite any file in the app store. So the context here was you would encrypt the file that you want, and then the file name would contain this / sequence. So when the file is decrypted by the application, this would overwrite the files, right? So another example, a PHP email iOS application. So the vulnerability here was on this part of the code. So it's basically concatenating the string escape for JavaScript, which was not escape for JavaScript, into the message of the body, right? So this is an application that was doing PGP using JavaScript. So it's first setting the private key, then setting the passphrase, and then on the message, you could email some user something like this, like colon, semicolon, and then some, JavaScript here to send the passphrase to some attacker machine, right? So you have the private key, the passphrase, and then you can get the passphrase and send it to an attacker the same way with the private key, right? So you could send the private key, the passphrase to an attacker using this attack, just sending an email to a user, right? So this is a very, very cool attack. And then the attacker would, of course, retrieve the passphrase like this, right? So this was a very nice attack vector. So now let's talk about an application very close to my heart, Smart Sheriff, right? So this application that I talked a little bit about at the beginning, called Smart Sheriff, mandated in the entire country of South Korea by law. Every parent and child is forced to install this application, controls phone usage, controls the installed application, block websites and stuff like this. So you can see the two public pentest reports there. The first time we tested them, we noticed that they were not using SSL for anything, so it was all clear text HTTP. So really bad. So we reported this, and the second time, it seems like they changed to SSL, right? Because they were using HTTPS. However, this is the validation of the SSL, right? So basically, when the application receives an SSL error, it's going to proceed anyway, and then when the host name of the SSL doesn't match, the verification process is just going to return true, and that was actually all the code, so just return true. So basically, if I have the certificate for 7security.com, I can use it to, for example, man in the middle google.com or facebook.com or whatever else, and this hostname verifier will say, yeah, that's fine, right? So it will, so that's basically the problem, right? So it ignores SSL errors, it ignores hostname mismatches on the SSL, certificate. So basically, it's the same as if you didn't have SSL, because anybody can man in the middle this with a self-signed certificate, and the application won't complain about it. Then the next problem that they had was that they had a hard-coded XOR key in the code, right? So XOR can be a secure algorithm, right? So there's, for example, the one-time paths, if you're familiar, um, during Second World War, I think. Sometimes this was used, uh, and it can be safe as long as the key changes every time and so on. However, in this case, we have XOR with a hard-coded key on the application, a hard-coded key on the binary that anybody can decompile and see, right? So this is basically stupid, because the server and the mobile app are sharing a key that is hard-coded on the app. So anybody can actually see this key by reversing the app. So there's absolutely no security in this, right? So the proper way would be to use asymmetric crypto, but in this case you have asymmetric algorithm with a hard-coded key on the application. And then we created basically a Python script with a hard-coded key to encrypt and decrypt using this. So basically, this was the name of the key. So Moiba was the company behind this. So this is the XOR key. So you have this, and then it goes through XOR with the key, and it gives you back the phone number, right? So this is the XOR key with some null bytes in there, maybe to try to make it harder to reverse. I'm not sure. And then the next time they added an AES layer. However, now AES is a good algorithm and so on, peer-reviewed and everything else. However, again, the key was hard-coded on the application, so you can see that the key is being retrieved from the application. So this again is insecure, right? So again, a secret between the server and the application that anybody can get a hold of by simply reversing the application without much skill. This is the other layer. We have another hard-coded key through AES. This is the encrypted request, and this is like the decrypted request. So it's basically a useless AES layer with a static key. So in summary, we have the phone number is encrypted with a first useless XOR key that is hard-coded in the application and everybody knows. So this is the encrypted phone number with the XOR key. Then this request is encrypted using AES with a second layer of encryption that is again useless because the AES key is again hard-coded on the phone, on the application. And then this request goes to the server. However, the SSL verification I showed you before is completely broken, so all failed all failed SSL errors are going to be ignored. So basically, anybody can man in the middle that. So this is all like completely useless, right? And then you get the response from the server back. So horrible security implementation is just it's worth summarizing the catastrophe in a slide like this. Now, this wouldn't be complete without talking a little bit about API attacks. So let's see a couple of examples. Retrieving files from the server, very classic attack where a developer believes that replacing dot dot slash with nothing is going to prevent path traversals. But what happens if you provide dot 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 slash slash? What's going to happen is that you provide dot 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 slash slash, and then this dot dot slash here is going to disappear with the string replace, and you will end up with dot dot slash, right? So you basically provide this in this fashion, and then when this is removed, you end up with a dot dot slash sequence, so you haven't solved anything, and you still have a path traversal problem. Very classic, web application security attack vector sometimes. Then uploading files to the server, another interesting scenario here. This was an application managing PGP fingerprints and so on. So it's running a command, and this is how it's running the command. It's basically joining the command here. It's using shell true, which is not recommended in the Python documentation. And basically this is being run in there, right? So this is like encoded and so on. So basically this is the curl request with the encoded payload, but basically you can just use the pipe character to run any command you want, like wget, whatever. So using this, we could, host a text file that contained a reverse shell, and then you can run curl to using the PGP fingerprint and the pipe character to do the wget of the attacker text file, and then run with bash the text file. So we have a shell, and then we got the reverse shell back, and we were already root, so we didn't even have to escalate privileges, right? So this was a very cool example. So yeah, was interesting. And then a cousin application of Smart Sheriff was okay. So this comes afterwards. So in every classroom, there's always this bad child that wants to mess with all the children, right? So this kind of bad kid that everybody hates and is afraid of in the class. So this kind of child wants to make the life of all the children in the classroom miserable, right? So for this kind of child, there was an API by Smart Sheriff called that we affectionately call the bully API. So basically, if you know the phone number of a child, you would ask, Smart Sheriff, I have the phone number of the child I want to mess with. Then the API will tell you, okay, this is the parent phone number. So with this, you can already do some damage, some prank calls, and so on. But as a bully, you also want like the password, right? Because to log in, you needed the parent URL, the parent phone number, but also the password. So you would politely ask Smart Sheriff, right? So you should always ask questions in life. So it will ask like, come on, Smart Sheriff, give me the password. And the API gives you the password with the XOR encryption that we saw before. So you got the API response with the password XORed, and you can basically log in as the parent of any child in the classroom. And from there, you can say this child can never use the phone during any time of the day, cannot visit any websites, cannot have any application installed, and so on, right? So this is how this looked in practice. And a cousin application of Smart Sheriff was Smart Dream. So this was flagging like dangerous words, like for example, if one child sent a message to another with a word like sex or something like that, then it would mark that as harmful, and it would save it into an API, right? So the problem with this was that was being saved in this server, and anybody could retrieve it, right? So let me try. So this was the Smart Sheriff demo first, basically trying random phone numbers. You can see that you get the parent phone number, the child, and the parent number, and then from the parent you get the password of everybody, and so on. And then the other one that I wanted to show is with Smart Dream. You calling the API, you could actually dump all the messages from the API that every child in the entire country of South Korea that was using this app um, typed, right? So this, now most of you probably don't speak Korean like me. So Fabian, who is the one that wrote this script, he actually replaced the original Korean characters with other characters. But the point is that you could actually dump all the messages from the API, and then you got like the phone number that wrote those messages and what the text of those messages was, right? So this was pretty bad. Yeah, so lots of bad stuff in there. And yeah, and with that, we have a couple of minutes for questions. Maybe I'll show one more demo, the alert, right? So Smart Sheriff, it was so bad that even Google indexed because the report is public, Google indexed the vulnerability. So you could actually search for the host, and then you get the alert was still working. This was, I think, like 1 year or more than 1 year after the pen test, and you can see that the alert is still working, and this is the actual injection in the page, right? So this was pretty bad. Okay, so with that, we have a minute or so for questions. So any questions before we wrap up? Now, this workshop, there's a longer version that is 4 hours, and all the vulnerable applications, the slides, and the longer, like more relaxed recording, 4 hours with more vulnerabilities than I covered today. This is all available for free. If you go to 70security.com/free, you can download everything from there, right? So You can watch the video, download the slides, download the vulnerable applications, and so on, right? So it's all available for free there. And if you found this interesting, maybe you can point some of your friends there so they can get this presentation and download everything and play with these demos and these apps. Just tinker a little bit and play with this, getting your hands dirty. Any questions before we wrap up? I don't see any question in the chat, so if there's no questions, there's a question here. Is there a way to get vulnerable application? Yes, this is all. Just click on the slides, and you can download all the vulnerable applications. So all the vulnerable applications that I showed today, they are on the slides. For all ones, there's a website called apicure.com. So apicure, I think, apicure.com or similar, for all versions. So there's some websites like this. I'm not sure if I misspelled, but it's called something like that. So this can be handy, like if you're looking for an older version of a specific app, sometimes you can find it there. Yeah, or APK Mirror. There's several websites. Like this, right? So, yeah, and the Chinese police apps and Smart Sheriff, these apps are part of our mobile course, if you are interested, right? So these are not as public or available with old versions, but yeah. So yeah, all this is available for free there. You can try this exercise on your own. If you run into any problems, you can email admin@7security.com and we will help you out with the exercise or give you some hints if you run into problems. So yeah, the slides, everything is available on this page. Yeah. So this is vulnerable apps to practice with, slides, recording. So yeah, it's all in there, right? So you can download it from there and play with the apps and so on. Okay, so if there's no more questions, we will leave it here. Thank you everybody for coming. Have a very nice rest of your day. Thank you everybody, and bye bye.